Hello students, welcome to the third lecture on blackbody radiation in quantum physics. Before I begin today's lecture, I would like to summarize what we have discussed in lecture 2. So in lecture 2, we have talked about how to design a blackbody in the laboratory. Then we have also discussed the experimental observations of the blackbody spectrum, where we have seen that for a given wavelength the intensity of radiation becomes maximum and the intensity remains very low for very low wavelengths as well as for very high wavelengths. We have also talked about the Wien's displacement law, which says that the peak wavelength and the absolute temperature of the body are inversely proportional to each other. Then we have discussed the Stefan-Boltzmann law, which says that the power radiated per unit area by a black body is directly proportional to the fourth power of the absolute temperature of the body. Now, in this lecture, I would like to discuss the classical laws of radiation which try to explain the blackbody spectrum, and those are the Wien's radiation law and the Rayleigh-Jeans law. But the classical laws fail to explain the blackbody spectrum, so we will also discuss about the failures of the classical laws of radiation. So at the time of the discovery of the blackbody radiation, the known concepts in physics were all classical theories of physics, like the classical mechanics and the classical electromagnetic theory. So based on this knowledge of the classical physics, the scientists tried to explain the blackbody spectrum. So first we will discuss the Wien's radiation law. Now, according to Wien's radiation law, the energy emitted by a black body in the wavelength range lambda and lambda plus d lambda is given by this formula, where A and B are constants. Now, if we just look at the plot of this law, so the blue curve here denotes the plot of the Wien's radiation law and the red curve denotes the experimental curve. We will see that at the low wavelength range, the Wien's radiation law can explain the experimental curve, but in the high wavelength range, the Wien's radiation law fails to explain the experimental curve because in the high wavelength range, the values of E lambda are lower than the experimental value. Then the next law that tried to explain the blackbody radiation is the Rayleigh-Jeans law. So in the Rayleigh and Jean, they made some assumptions for the derivation of their law. So here you can see is a picture of the black body cavity, and where we know that once radiation enters through the the orifice of the black body, the atoms inside the black body, they get excited and they start oscillating, and therefore they emit radiation. So the assumptions of Rayleigh-Jeans law were that the cavity walls are made of atomic oscillators, and according to classical electromagnetic theory, these oscillating particles radiate. Now, since they are emitting electromagnetic waves, the superposition of electromagnetic waves inside the cavity generates standing waves inside the cavity. So this was the second assumption of the Rayleigh-Jeans law. And the third assumption was that the average energy of the oscillators will be calculated from the theorem of equipartition of energy. So Rayleigh and Jean calculated the number of modes of the standing waves within the frequency range nu and nu plus d nu as this, where the c is the velocity of the electromagnetic wave. Now, what is the theory of equipartition of energy? Based on this, Rayleigh and Jean calculated the average energy of the atomic oscillator. So, the theory of equipartition of energy states that for a system of particles in thermal equilibrium at temperature T, the average kinetic energy of a particle per degree of freedom is half kBT, where kB is a Boltzmann constant. So now the atoms inside the walls of the cavity, they will have 2 degrees of freedom because their motion is restricted on the surface of the wall. So according to the theorem of equipartition of energy, the average energy of each atom will be given by kBT, and it is represented by epsilon bar. Therefore, the energy density corresponding to radiations in the frequency range nu and nu plus d nu is given by u nu d nu equal to n nu d nu into epsilon bar, where this n nu d nu is the number of oscillators per unit volume that contribute to the radiation of a given frequency range, and epsilon bar is the average energy of an oscillator at an absolute temperature T. So now if we put the expressions of nu, d nu and epsilon bar, then the energy density in the frequency range nu and nu plus d nu looks like this. Now the relation between nu and lambda is like this, that C by lambda is equal to nu. So d nu will be given by this, and since u nu d nu is the energy density, it should remain positive. So we have taken the mod of this expression. So the energy density in the wavelength range lambda and lambda plus d lambda will now be represented as 8 pi by lambda to the power of 4 kBt d lambda. So we have represented the energy density now in within the wavelength range lambda and lambda plus d lambda. So therefore, there is a relation between the energy E lambda in the wavelength range lambda plus d lambda and the energy density U lambda, and that is given by this. E lambda d lambda is equal to C by 4 into U lambda d lambda. So the expression of U lambda d lambda, if we just put over here, therefore we get the energy that is being emitted in the wavelength range lambda and lambda plus d lambda, and that is given by this expression, and this is what is called the Rayleigh's law. So now let us see that how the plot of Rayleigh's law will look like. So this is the plot of the Rayleigh's law, and this is the plot of the experimental data. And we can well see from this graph that Rayleigh's law could not explain the blackbody spectrum properly. So if we just look at the graph, we will see that Rayleigh's law could explain the experimental spectrum in the long wavelength region. So here this blue curve is the experimental curve, and this is the Rayleigh's curve, and we can see that it could explain the spectrum at the long wavelength region, but in the short wavelength region it failed to explain the spectrum. Because according to this formula, when lambda tends to 0, this E lambda d lambda should be infinite, and that is what is shown in this curve. But in the experimental curve, we know that when lambda tends to 0, E lambda d lambda should also tend to 0. So the law fails drastically at the low wavelength region. And since it fails in the ultraviolet region, therefore this failure is called the ultraviolet catastrophe in physics, and it is a very popular term in physics, the ultraviolet catastrophe. So as we can see that the classical theory failed to explain the blackbody spectrum. So if here is a comparison of the Rayleigh's formula and the Wien's formula with the experimental curve, and we see neither the Rayleigh's formula nor the Wien's formula could explain the experimental curve properly. So this led to the beginning of quantum mechanics. So this led to the revolutionary concept of Max Planck. In the next lecture, I will discuss about the Planck's quantum hypothesis, and we will also talk about the Planck's law of radiation, and we will see that it is this Planck's law of radiation that could explain the blackbody spectrum. So with this, I end my lecture today. Thank you.